Swayam Prabha. Digital India. Educated India.
Welcome to lecture 4. Today I am going to speak about some properties of ideals and some examples of ideals, how to construct ideals in a ring. So, all these things we are going to cover today. So, in the previous lecture I have defined what is an ideal, and today I will give you how to construct an ideal in a ring. So, we have seen that we have define the ideal by generalizing the notion of the kernel. So, this kernel of a ring homomorphism has some special property that we have generalized for any arbitrary set, and that is how we have constructed the ideal. So, now today we will try to see how can we get examples of ideals. So, one of the way is to construct a ring homomorphism and see what is the kernel of this ring homomorphism, and you can construct a example of ideals from that ring homomorphism, because kernel of any ring homomorphism has the structure of an ideal. So, let us start. So, let me start with this example. So, suppose I have this map phi from the polynomial ring Rx, sorry, not in Rx, from Qx to R. So, Qx is nothing but the polynomial ring with coefficients from the rational numbers. In fact, we can define a polynomial ring over any arbitrary ring. Here previously we have seen polynomial ring over the field of real numbers. Now, we are observing polynomial ring over the field of rational numbers. So, how I am defining this map? So, the map is defined. So, phi of fx is a polynomial over qx. So, that I am sending it to evaluating this polynomial at root 2. So, of course, this will be a real number. So, now it is not this is basically an evaluation map, you can see, and you can check that this is in fact a ring homomorphism. So, it is a ring homomorphism. Now, let us see what is the kernel of this ring homomorphism phi. So, the kernel is nothing but all the elements, all the polynomials in the ring Qx such that root 2 is a root of that polynomial. So, all those polynomials which vanishes at root 2. So, that means root 2 is a root of this polynomial fx. Now, since this polynomial are having coefficients over the rational numbers, you can say that no polynomial of degree 1 can have a root as root 2. So, that means if the polynomial is in the kernel, then its degree has to be greater than equal to 2. So, note that any polynomial in the kernel cannot be a linear polynomial. That means it has to be a degree greater than equal to 2 polynomial. Also, I can see that I know that root 2 is nothing but the root of which polynomial x square minus 2. So, if I consider the polynomial x square minus 2, this is a degree 2 polynomial, which is the smallest degree polynomial such that root 2 is a root of this polynomial, and this polynomial belongs to the kernel of phi. So, that means if I consider any multiple of this polynomial x square minus 2, then that will also be in the kernel. Therefore, this all the multiples of x square minus 2 is in fact in the kernel. Now, I will show that any element in the kernel will be in fact a multiple of x square minus 2. So, let gx be any arbitrary polynomial in the kernel of this. That means, if I evaluate g at root 2, then it will be 0, that is by the definition of this kernel. And if I now apply division algorithm on this gx, means if I divide this polynomial gx by the polynomial x square minus 2, then what I can write? So, by division algorithm, we can write gx as some multiple of x square minus 2, say with qx plus rx, where rx is nothing but the remainder term. So, there are some restriction on the remainder term, where degree of rx will be strictly less than 2, or so either this condition holds, that either degree of Rx is strictly less than 2 or Rx has to be equal to identically 0. But now from this equation I can rewrite my Rx as g of x minus x square minus 2 into qx. Then you can observe that this is already in the kernel that I have started with. X square minus 2, this is also in the kernel. So, any multiple of that is also in the kernel. And since kernel has already a subgroup structure, therefore, this difference is also in the kernel. Therefore, this Rx is in the kernel of this map. But Rx is a polynomial whose degree is strictly less than 2. But we know that we cannot have any linear polynomial whose root will be a root 2. Therefore, this leads us that Rx has to be equal to 0. So, this implies that R evaluated at root 2 has to be equal to 0, which is not possible, as no linear polynomial can have root 2 as a root, which implies that Rx has to be equal to identically 0. So, that gives me that this kernel of phi is nothing but the elements will be all multiples of x square minus 2. That means that we have seen that gx will be of this form, where Rx has to be equal to 0 now. So, therefore, gx is nothing but the multiple of x square minus 2. So, therefore, this kernel is having this structure, that x square minus 2 into qx, such that this qx is varying over all the polynomials in the ring qx. Therefore, we have seen here that this kernel of phi, which is in fact an ideal, which is arising as the kernel of a ring homomorphism, is nothing but all the multiples of a particular polynomial x square minus 2. So, this is one of the example of an ideal, but we can in fact create some more ideals even much more easily. So, let us see how we can do that. But now onwards, I will assume that my ring is a commutative ring. Now onwards, I assume that my ring is commutative. Sorry. So, all the rings are commutative. So, let us now define how we can construct ideal. So, let A be any subset. So, let A be any subset of a ring R. So, R is a ring and A is any subset. So, by this notation I denote the smallest ideal containing A. So, this denote the smallest ideal containing A, which is called the ideal generated by A. So, how does it look like? So, the ideal generated by A will be of the form. So, the elements will be nothing but finite sum, finite linear combination. So, R1 A1 plus Rn An such that these Ri's are varying over the ring R and Ai's are elements of the set A, and this n is nothing but a positive integer. So, if I start with a collection, I start with a subset of R, then what does it say? It says by this notation I mean the ideal generated by A, which is nothing but the collection of the elements of this form, which is nothing but the linear combinations of the elements of the set A with coefficients coming from the ring R. Okay. And this n is any positive integer. So, all the finite collections I am considering with coefficients from the ring R and Ai's from the set A. So, this is the ideal generated by A, and it is in fact the smallest ideal which contains this set A. Now, in this one, if I assume that this A is generated by A, this subset A has only one element, in that case the ideal is generated by a single element. So, an ideal generated by a single element, that is if A has a single element. In that case, we call that ideal is a principal ideal, is called a principal ideal. So, if you having an ideal which is generated by a single element, so that means how does it look like? So, let us see. So, let this set A has only one element A, then the ideal generated by A will be of the form R times A such that R is such that R is varying over all the elements of the ring R. So, this is called a principal ideal. So, the principal ideal look like is of this form, and if this A has a finite, A is a finite set, that means we have finitely many generators, then it is called a finitely generated ideal. So, an ideal generated by a finite set generated by a finite set of element is called a finitely generated ideal. That means suppose in that case I have this set A has finitely many elements A1 up to AR, then the ideal generated by A is also denoted by the ideal generated by A1 up to AR is nothing but the collection of the elements of the form R1 A1 plus R. So, maybe this is not a good notation. I will just change this R to N. Change this R to N. So, then this is Rn En. So, this where this Ri's are varying over the elements of the ring. So, this is how we define an ideal generated by a finitely many element. Now, in any ring there are two ideals already there. One is the 0 ideal, another one is the whole ring. So, in any ring R, there is the ideal which consists of the singleton element 0. That means the ideal generated by 0 and it is generated by 0 and denoted by this notation. So, we have by default in any ring there is this ideal which is generated by 0 that is having only one element and that is known as the 0 ideal. Apart from this 0 ideal, there is this whole ring is also an ideal. The whole ring is also an ideal and this is called the unit ideal and it is called the unit ideal. In fact, we can see that this ideal is also generated by a single element and that single element is nothing but the identity, multiplicative identity element and which is generated by 1 and is denoted by the notation 1, generated by 1. Now, as a remark, I would like to mention that if you in a ring, we have already introduced the concept of unit element. If an ideal contains a unit element, then it is in fact becomes the unit ideal. So, that means that it will the multiplicative identity then belongs to this ideal. So, how to show that? So, if an ideal contains a unit element, then it is the unit ideal. Then it is the unit ideal. Why is that? So, let A be any element in this ideal I be an unit element. That means that there exists, which implies that there exists an element then it implies that there exists some element B in R such that if I multiply A with B, then I will get the identity element. But now this belongs to the ideal generated by A, because AB, any multiple of A also belongs to the ideal generated by A. Therefore, AB belongs to A, that means the unit multiplicative identity belongs to the ideal generated by A, which implies that the ideal generated by A is nothing but the unit ideal. Therefore, if an ideal contains a unit element, then it is in fact the whole ring, which is nothing but the known as the unit ideal. And also, as a remark, I would like to mention that an ideal is said to be a proper ideal if it is not the zero ideal or the unit ideal. So, which is not the zero ideal or the unit ideal is called a proper ideal. But here another important thing just to note, that it very much depends on which ring we are considering the element. So, for example, if we are in the ring of integers and consider the element ideal generated by 5, then this ideal, the elements of this ideal are nothing but the multiples of 5, right. So, where n is varying from all the integers. But if I consider the same ideal in the real numbers, this is also a ring, then in that case I can see that this is nothing but the unit ideal, because this 5 is a unit element in R, because 5 is an unit element in R. It has the multiplicative inverse, 1 by 5 is there. Therefore, it depends on very much that which ring we are considering, whether it is an unit ideal or whether it is a proper ideal. In Z it is a proper ideal, whereas in R it is the unit ideal. Now, the next question we would like to see is that if we are in a field, then the question we would like to ask next is that, can we identify all the ideals of a field F? That means, how does the ideals of a field look like? So, of course, in any ring we have by default two ideals, one is the unit ideal, another one is the zero ideal. But in a field you can observe that every element is a unit element. Therefore, in a field, if I take any non-zero element, then it is a unit element. Therefore, the ideal generated by that element will become nothing but the unit ideal. Therefore, the field has exactly two ideals. So, that I will put it as a proposition, that the only ideals in a field are the zero ideal and the unit ideal. Zero ideal and unit ideal. So, we have seen that we have exactly two ideals in a field. Now, we can ask the converse, that if in a ring you have exactly two ideals, then is it a field or not? And the answer is yes. So, let me put it as a proposition, this fact. So, let R be a, let R has exactly two ideals. Maybe not in this way. Let R has exactly two ideals, then I will prove that R is in fact a field. So, if a ring has exactly two ideals, then it is in fact a field. So, let us see the proof quickly. So, first we will see that in this ring R we have that multiplicative identity is not as the additive identity. So, if multiplicative identity is same as additive identity, then R is the 0 ring, and so it has only one ideal. But it is given that R has exactly 2 ideals. Therefore, the multiplicative identity is not same as the additive identity, as R has exactly 2 ideals. So, now I would like to show that R is a field. So, I have this unit ideal and the 0 ideal. Now, I would like to show that every non-zero element has an inverse. So, let B be a non-zero element in R. Then I would like to show that it has a multiplicative inverse. Then if I consider the ideal generated by B, then it has to be the unit ideal, because the ideal B is a non-zero element. So, it cannot be the 0 ideal, but I have only 2 ideals. So, it has to be the unit ideal. So, that means B belongs to the ideal generated by 1, which implies that there exists some A in R such that AB have to be equal to 1. This implies that B is a unit element. Therefore, it proves that R is a field. So, I have proved that if you have a ring which has exactly 2 ideals, then it is in fact a field. Now, the next thing that I would like to prove is the following. So, let F be a field and R be a non-zero ring. Then it says that every ring homomorphism phi from F to R is injective. So, if you have, so a field has also a ring structure. So, if you have a ring homomorphism from a field to a non-zero ring, then it is in fact a injective ring homomorphism. Why is that? So, we will be using the structure of the ideals of a field. So, we know that kernel of phi is an ideal of the field F, and the field F has only 2 ideals, 0 ideal and the whole ring, but F have 2 ideals, 0 and the unit ideal. Now, if kernel of phi is the unit ideal, in that case what will happen? In that case R will become the, then R will become the 0 ring, then R is the 0 ring, because then multiplicative identity of R and additive identity of R will be same, then R will become the 0 ring, which is a contradiction, because it is given that R is a non-zero ring, which is a contradiction. Therefore, I should have that kernel of phi is nothing but the 0 ideal. So, kernel of phi is 0 ideal means that the map is injective. Thus, phi is an injective ring homomorphism. So, we have observed that if you have a ring homomorphism from a field to a non-zero ring, then it is in fact a injective ring homomorphism. Now, next time we will be discussing about how does the structure of the ideals in the ring of integers look like, or how the structure of the ideals in the polynomial ring over a field look like. So, today I will stop here, and these are the references that I have used for this today's lecture. Thank you.